Let's see my screen. Yep. Okay. Cool. That's LabView. All right. So today I'm going to talk a bit about. Okay. Come on. Yeah. I'm going to be talking about making sense of LabView and FRC. Who am I? I don't know, Mr. Florence gave me an introduction in another section, but I'll do it myself here. I'm a graduate student in mechanical engineering at Purdue University. I'm a PhD student. I'm a tenured PhD student because I passed my qualifying exams this semester, so I'm in it to win it. My specialty areas are numerical optimization and analysis, machine design, mechatronics, and control systems. So, in my specific area right now, I'm working on some research projects that are funded by some companies, and I'm working on laser printers. This is an inkjet printer that will be being a little poke at today, but mostly laser printers for me. I work on making them better, faster, and stronger, and while doing so, clearly, as you may be able to tell, I do listen to a little bit of Daft Punk. And I use LabView for some of my research. It's very common in the real world, or in the industrial world, for building instrumentation and control systems, especially for low volume things. So if you're at a company and you build a cell to test your engine or something like that, a lot of times it's done with LabView, and actually, specifically with a compact RIA, not dissimilar from this. It may be a different model or version, but it's the same guts. So the topics today, I'm going to talk about some basics of LabView. We'll talk about DIs, we'll talk about variables, we'll talk about yada and the other yada. And then we'll talk about when things happen and what makes LabView different from other programming languages, which is namely data flow and how execution is controlled. We'll talk about troubleshooting tools, and we'll talk about getting stuff on a robot. As you can see, as it wasn't before, all the lights are blinking now on this thing, so I think we're good to go. Well, it says I don't have communication. We'll figure that out later. I don't know. Hopefully we'll be able to use that. I will do some LabView up here too. So let's talk about the basics. So LabView is a programming language. It's actually a fully fledged programming language, unlike many other graphical languages, which aren't really complete. LabView is a complete language. Historically, LabView was designed by NI, National Instruments, which is a company out of Austin, Texas, I believe, to make life easier for engineers and scientists wanting to put together instrumentation. Basically, they used to make a bunch of like PCI cards and stuff you could slot into your computer, and it would have analog reading and analog output and all these inputs and outputs that you could use to measure and control whatever you were building. But at that time, you had to program it all in like C or whatever. And most of the people who wanted to build these systems were just physicists and scientists or engineers who weren't necessarily computer people or computer engineers or computer scientists who didn't necessarily want to spend all this time learning how to make this thing work. So they wanted to come up with something a little bit easier. It's meant to be easy to use, but we can't program it exactly like C or other traditional languages. It is a data flow, but not a procedural language. So LabView has the peculiarity or particularity or whatever you want to call it of having, it's because of that lineage of being arranged into two main components. You have a virtual instrument, which is a program or a subprogram, and then that program or subprogram actually has a front panel and it has a block diagram. And the front panel is indicators and controls. It's very useful. You can put buttons and LEDs and graphs and dials and everything you want on it. And the block diagram, this is where the code goes. I'll show you what that looks like in just a moment. But first, let me talk a little bit about some variables and signals that you'll see. So variables and signals in LabView travel on wires. There are basic types like Boolean, which is just a true or false value signal. And then you have a numeric signal, that would be an integer. And so that'll be designated by a blue wire. The Booleans are green wires. And And an integer is a numeric is an integer number. It'll be, let's say, 1, 2, 3, or 5,390,584. And we also have doubles. So double is a 64-bit floating point decimal number. So you can represent quantities like shown here. That's orange wires. We also have strings, which are collections of characters that travel together, like a word or a sentence. And those are represented by pink wire. There are many more types, and we'll talk a little bit about them, but let's just wait. So a little quick quiz. I love LabView in pink is an example of a string. How about 0.4234 in orange?
Double.
Double. Awesome. Wow. I think so. I switched the slide format, so everything moved around, but I guess the arrows didn't. That's a double. You guys got it right. I got it wrong. You guys know this better than I. Ta-da! Okay. All right. So let's take a look at what this front panel stuff looks like. Okay. So here's PowerPoint, and here's LabView. So let me just create a new VI. Now I'm just creating it right here. This will actually run on my computer. And so here we have our front panel, called Untitled 1. And Untitled 1 has a block diagram. This is where our code goes. This is where our front panel goes. So I can actually do something. Let's do the simplest thing. I'm going to put in a toggle switch, right? So this is on or off. And then I'm just going to put up an LED, which is LEDs either on or off in LabView. So I'm just going to say this is another Boolean thing. So I can say it's Boolean, on or off, output. Okay, great. Now, if I just run this, nothing's going to happen. Right? And actually, one thing is nothing happens because nothing is actually connected over here. There's no flow of this signal over to here, right? So what I need to do is just attach them. Just click, click, attached. Ta-da! I've programmed a computer. So now if let's say I click this thing and I turn it on, right? And I hit this button, ta-da! Now it calculates it. It calculated that it was on. That switch was on. If I click it again, I calculate it was off. Now you can see that I'm having to click run over and over again. In this case, I can do something like run continuously, and now when I do this, it'll... Sweet, we wrote our first program. We can turn on a light with a switch. So we're getting there. In reality, on the robot, things work a little differently, and we'll get to that in a moment. Run. There. Okay. So when do things happen? Well, we saw that kind of peculiarity that it wasn't running all the time if we had run, and we had to run continuously. So the first thing to kind of worry about, though, is that things happen in order, but sort of, not like you would expect. Things don't run front left to right, or right to left, or up to down, or whatever. There is no spatial dependence of how code runs. If you're writing in C or Python or one of those more traditional languages, things run in an order. They run top down on the page, right? Well, unless you have functions and you're jumping back and forth. But in general, they run up and down on the page, or just up to down and left to right. But what happens, to that order when you just have things strung together? And let's look at it a little demonstration. I don't want to load up because it takes forever, but okay. So let's come in here. Let's delete our guys, right? So let's say I have I'll just tell you how it works. Okay. Okay. So I have this example here. We're going to use this quiz example as our understanding of how it works. So what happens is something very interesting. A piece of code, like this multiplication, is a piece of code. And this square root is a piece of code, and this addition is a piece of code. A piece of code only executes when all of the data for that piece of code is available, right? So do I know which of these inputs it's going to read first? No, I don't. And the way the language works, I'm not supposed to care. I'm just supposed to not work around that, but be cognizant of that. But I do know, for example, that this will always occur before this. But here I have this dice here, and this basically says generate a random number. And so I'm going to basically add these two things, take the square root of the addition of those things after you do it, so that's the order of that. And then I want you to multiply this by this. Now, when does it generate the random number versus doing the square root or any of this stuff? It may actually read this after this, after generating that random number. It may generate this random number, read this, then read this, and do this. It may actually generate, or it may actually do this, 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 and then generate the random number, then square root this. I actually don't know, but I don't care as long as things get out here in the right amount of, together. And then the language makes sure, the program will make sure that that will happen. Is that clear to everybody? That there are certain situations, and you just need to be cognizant of that. And there are a lot of, I have kids who will come to the team and then they will start programming, right? And then they won't know this, and they'll say, oh, I got it. I was like, okay, if you read all this stuff, then you should know that it's day of and that doesn't have, they don't like to read. They just like to click. So they do it, and then they come up and they're like, this is like, why doesn't this work? And I'm like, that's just how the language is. There are tricks you can play to make things go in a certain order. We'll talk about that. But in general, why should you worry about it? I don't know. So execution control, there are other things we can do in execute. And we can have loops. So a loop continues until a condition is met. We can do for loops. A loop runs a number of times. And then we can do some modifications on that. We can put in waits and delays. And we can put in timers in a loop, so we can do, so let's say we need to, every 1/10 of a second, I need to read an input and compare that to something else and do some action based on that. I can do that pretty readily. The other part of execution control is case statements. You use those to switch between possible code branches. And then we have Boolean operations, which are logic operations, like and or that sort of thing. And you can chain those to comparisons. Okay, so let's look at an example of a loop. So one example of a loop, the simplest thing we could do, is I'm actually going to undo that delete operation, because I like this guy. This is pretty sweet program. But I only want to hit run once, and I don't want to use run continuously. So what I could do is I can set up a while loop and see it already generated this little control here that says stop. Let's see what that looks like on our front panel. There's a little stop button here. I'll pull it out here. So you can arrange where these things go. You can make it as nicely laid out as you want. And now I can actually hit run, and now what will happen is it's automatically doing that loop, right? And works the same as before. Now what is it doing right now? It's actually, I haven't put any time or waiting period in this loop, so what does it do? It runs that loop as fast as it can, which I might not want to do because that burns a lot of processing power to just continuously check everything. So let's say I only want it to run every once in a while. So, where does that live? Execution control. Programming, timing, and I can go to something like wait milliseconds, and then here I have an input. It just says milliseconds to wait. One of the cool things about LabView is I can actually right-click on a given input or output, and I can pick out, so here it shows me the most recent palette that I looked in. It shows me some numerics that I might be interested in timing. And then it gives me this create thing, and I can actually create constants or controls or indicators based on that. So let's do a control. So let's, and it all nicely named it for me, so there's milliseconds to wait, right? Let me pull this out here. Now what I can do, let's say I save 500 milliseconds. What does that mean? It means this loop is only going to run once every half second. So if I click this and I say run, you see there's now a time lag until the next time it actually checks. It's only checking it every half second. So now there's a time lag when I click. If I line it up correctly, there's no time lag because it hits at the right time. But in general, this saves a lot of processing power if I don't need to use it. There's also another type of loop, and I can replace this with a timed loop. You can also draw the time loop in the same way. And in this case, I don't actually have to do the milliseconds here. And see here, it says I have a clock that's coming into it that's at 1 kilohertz, so 1,000 times a second. And here I have a time delay, or how many clocks every, or what the period of execution is. Here I can create another constant. It'll do, and let's say, let's do 750, because, and now suddenly, it's a little slower because it's 750, but it's doing the same function. Now, why would you use a timed loop instead of a wait loop? Does anybody know?
Time is going to already have all the functions in it, so you're going to have less code involved in it?
That's very true. The other thing is actually a little more subtle. The other reason is a little more subtle. And if did any of you guys go to Keith Hall's feedback controls one? I guess if you came to the electronics one, you didn't come to that, but you went to Keith's, right?
Yeah, I was going to actually ask a question. So
Okay.
if you have, is my idea of the difference between the two is, does this one check the time constraint before it executes or after?
That is very astute. This one, it's not exactly like that, but this one basically makes sure that every 750 milliseconds it executes, okay? Whereas the other one has two tasks that run in parallel, right? So if I, I'm going to undo and go back to that one, right? Okay, right? So what is going on in here? We talked about the execution stuff, right? Now we do know from that discussion that this evaluation and this evaluation, well, we only have one processor, so they have to be done sequentially in some way. We don't know which one's going to happen first. We do know that the loop is going to elapse in some way, right? And so I don't, the other thing is, if this stuff that's here parallel with this takes a long time, let's say this is a huge amount of processing, it takes even like 10 milliseconds, right? And I'm on a 100 millisecond timer for my loop. Then it has to do this, and it has to do this, and then it can repeat this loop. So then my loop is actually running at 110 milliseconds, which is not actually what I expected. And if you have branching statements in here, like if statements, and it could do a variable amount of processing time, right? So it might spend 105 milliseconds in this loop, in each cycle. It might spend 120 milliseconds. It might spend 175. Now, you might say, oh, well, okay, who can beat that, right? But what happens is, if I'm running, this comes from my control engineering side, is that if I'm running something like a PID controller, right? That gain that I pick, the best gain that I pick, is actually a function of a couple of things. It's a function of the physics of my problem, of my machine, but it's also a direct function. What it should be for the same behavior is a direct function of the time delay between loop iterations. So, and in certain cases, that ideal P should be, proportional or related in that way to that time delay. So that the ideal gain will change, so the behavior will actually not be what I expect.
So if you're sensing and dodging bullets, it might be important.
Right. Now, it may even be important if your loop is running slow enough compared to the speed of your mechanical system. So if I have a very fast mechanical system that I can control very quickly. So in a robot, the main ones you'll see are like, if I'm around my operating point for like the speed of a shooter, I'm trying to control the speed of a shooter. I can, at least for small amounts, control my speed pretty accurately and quickly with the motor because it responds really fast because there's not a lot of inertia on there, right? So if there's not a lot of inertia there, then the speed at which my mechanical system responds is quite fast. And if the speed at which you sample your loop is relatively close to that, within a couple times of that, then this sort of behavior can actually cause unexpected effects. In the control engineering parlance, you would call it, if I'm running close to my Nyquist frequency, this can cause a huge number of problems. So, in general, it does take a little more processing power to run the timed loop because it blocks out periods of time and says, I am going to run this thing here. So anything else, my camera code has to wait, this code has to wait. And you'll notice if I do some control shift these, I guess is what it is. You'll notice that there's a cool little thing here. And if I put my mouse over it, on this processor, it's this priority thing. So you can actually set the priority of this loop and say, this loop is really important, you need to run this faster or at better timing than this other stuff.
Well, before anything else.
Yeah, you can say run this before you run anything else. You don't want to do it too much because...
It's really taking advantage of the real-time operating system.
Absolutely.
If you say this has to happen at this time, it's going to happen regardless of what else is going to happen.
Yeah. So you have to be a little careful because it can cause other unexpected behavior in the code that isn't so high priority. But in general, this is what you might want to do. So I'm just actually going to maximize this because for whatever reason it takes a while to switch. So I'm just going to position slide this way, if you don't mind. Okay. So we also sometimes want data to travel together. So you can basically have arrays which are bundles of data that's all the same type. And you can have multiple direct dimensions. So you could call them vectors, and you can call them matrices, and you call them cube, or I don't know what they're called when you go to more dimensions than matrices. Cubes, I think of a cube of data, I don't know. Clusters are multiple different types of data. You can have like a a double and an integer and this thing, and you can say all of these belong to one cluster, and that cluster is like some related quantities, say the speed and some other information regarding your shooter, and whether it's on or not, that sort of thing. And then there are type definitions. I'm not going to cover them very much, but the actual like object-oriented programming, if you're familiar with that. Modularity. Sub-VIs are basically sub-functions that you can make, and I'll show you a little bit of that. They're very helpful in keeping code really clean. Be careful that you know how they will behave, especially when you put loops in those sub-VIs, because they will maybe act differently than you expect. Now what happens in parallel loops? So if I have two loops in parallel, sometimes it gets tricky. You don't know when each iteration of each loop will happen relative to the other. So there are simple examples of variables, and you can basically have local variables, and they will stop two loops and start them at the same time, that sort of thing. What I like in terms of, I'm just kind of going through this basic, this stuff, and then I'll go through some more demonstration stuff. I think that'll be easier, hopefully on this computer. Problems you can have, your algorithm can be bad, your timing may not behave the way you like, and you can have race conditions. So there's a couple of things you can do in diagnosing problems. One is called probes. So if I come over here, I can pull up, I right click on a wire, I can say probe, and what will happen is it brings it, and this will work on the compact reel as well, but it brings up this thing, and so it says probes, untitled 1, and so it's in Untitled 1 and it's probe 1. And so if I run this thing again, right, see it's continuously running. And now you see that it says true, right? And now if I flip this on, the probe actually watches what the value is. So even if I didn't have this feedback, I could look at the probe value and see what it is in real time, which is kind of nice. Another thing you can do is what's called execution highlighting. I'm going to show you some of this stuff. So that's easier to see. You can click this guy, this little light bulb button, and what it'll do is it'll slow everything down and it'll show you how things are running. So you can see how the different things are moving on the wire and when they move on the wire. And you can see that the loop is working. You can see the values on each of these variables. So here it's 500 milliseconds, here it's true. Let's switch this thing. Then the next loop around it will change to false. So you can use this to slow your program down and see what things are doing. That one is really helpful. The other thing that is really awesome in LabView is plots. So here I can do something like, what I'm going to do, I'm going to just generate a random number, or just pull out a number from somewhere. Here it's going to generate a random number from 0 to 1. What I can actually do is I can come over here to my front panel. You can name all these things nicely, just by double clicking on this stuff you can rename it. In the interest of time, I can actually make a chart. And let's say this variable was something from my robot. I can actually grab this chart and it just pulls it out here, and I can actually grab number, I can hit go, and then every 500 milliseconds, it'll be really slow because highlight exclusion, I'll turn that off. Every 500 milliseconds, it's going to generate a random number, and now I can see the progression of that value over time. This is really useful in trying to see what your robot's doing, because then you can get data that's like very quickly visualized. It's way easier it's even easier than plotting in Excel, because here you just right-click and drag a line into it, and now I have a beautiful plot. So it's pretty handy. You can do multiple lines on the same plot and all that stuff as well. So those are my three big things for troubleshooting. You should also design code to avoid problems. You use the simplest code to accomplish a given task. Think about the code before you start programming. In LabView, because of the data flow, maybe flowcharts and pseudocode are not always the best idea. Sometimes you want to work backwards. Just kind of depends on how you work. I mean, I guess I should say that the normal method of doing step-by-step flow charts and pseudocode may not always be the most intuitive with data flow. So I do flowcharts and pseudocode, except oftentimes I work backwards or forwards and backwards and backwards and forwards and try to figure stuff out that way. And it's good to practice on simple examples. If there's a piece of code or a built-in function you haven't used before, do it in a controlled environment so that you can understand the behavior. And then dealing with timing problems, so LabView is implicitly and unavoidably multi-threaded. This is kind of neat because when you look at people who look at C code and all this stuff and they talk about, man, I wrote this multi-threaded program and it was so hard and I built all these semaphores and all these different parts of the program are talking back and forth. You don't have to do that here. It automatically does it. I don't know when it's going to do the different things, but it'll take care of it automatically. I don't really need to worry about it. But when you do want to control the timing explicitly, you can use queues and semaphores and error clusters. And you can also use advanced code structures like state machines. I don't have a huge amount of time today, so we'll see how much I can get through. I'll try to get through all these slides, and then we'll talk about some of the more advanced stuff. So what about the robot? Okay. First, NI and WPI have collaborated really nicely to give us a great setup. They have dashboard. There's a dashboard on this computer over here. And I just realized why it didn't have communications. This cable was hanging out. So, there's usually a lot of good. Yep. Communications and robot code. Good. It says it doesn't have any joysticks, which is understandable. Yeah, so they built templates to get the code started already. I'll go through them just momentarily. And what does it look like? It's pretty much the same as that program that we've been messing around with, except a lot bigger. I'll show you the components of that program. But there's a big focus on determinism, which is generally what you have to worry about working on a real-time embedded device versus working on a computer, right? If I'm writing a code for a website, right, it'll take however long it needs to run. We'd like it to be reasonably fast. In this case, if the field management system says shut that thing down because that robot's going to crash through the field wall, it needs to shut off pretty quick. If you're if I were building something in my lab for a robot and a big robot arm, and I build in safeguards so that if somebody hits that emergency stop button, it needs to stop as fast as possible. So you have to really worry about that determinism and timing. And then the robot stuff does tie into the field system. It manages teleop mode versus autonomous mode. There are two components to the robotics around. One is where the robot is acting on its own. The other is when it's in teleoperated control with joysticks and whatnot. So how do we tie things together? Well, you can explore the libraries, both the NI ones and the ones that are provided by FIRST. And we're going to look at reading encoder and plotting that motion. I don't think I had a demonstration with an oscilloscope to compare timing accuracy, but I don't have that today. But we'll do some other stuff instead. So I'm going to switch over to my computer that is running the FRC LabView. Do you guys have any questions so far? Yeah. Go ahead.
Yeah, so if I'm trying to explain LabView to someone who's really used to like procedural programming, could you say a sub VI is like a function
Yeah.
or just such a thing not?
No, it's a function.
Okay.
So that's a fair description.
And then a VI would be the general file?
Well,
Or is that, or can we say
that's
that it's a large function and then it's consistent of a smaller function?
right, yeah. I think that'd be a better. It's not necessary that a VI has its own file, depending on how the file structure is laid out. You can have them I believe you can have them embedded into projects so that they don't have their own files. But I could be confusing LabView and SolidWorks. But yeah, it shouldn't be. I think the functional description is better rather than the file description. Okay, so let's see if we can get some connection going. I hate this part. I hate that part so much. Come on. So it's going to take a second. Or more than a second. So you can see already, so I've started a demonstration project. I actually haven't removed or taken out any functions. So it's saying there's stuff running on there already. Well, that's fine, I want to write over it. So here, it's divided into these sections. There's team code. This is all subject to change next year, depending on how they want to do it. We have this team code. We have a begin VI. This is all the code that runs at the very beginning of the match. We have autonomous stuff. This stuff runs during autonomous mode. The stuff that runs in teleop mode. There's stuff that you can set up as a test file. So you put test code here. This is a structure called a state machine. I'll talk about that briefly. And you just double click to open any of these. Some of them are embedded in others, and I'll show you that. So let's look at, so the main top level one is VI is called Robot Main. This is the one that runs everything. So in Robot Main, let me close all this stuff so there's not distracting. Okay, so Robot Main has this front panel, and that's basically all there is. It may have an image or not, depending on what you're doing with the camera. So you can hit Control E or go to Window, Show Block Diagram, pull up the block diagram window. So I'm going to hit Control E. And so this is what a block diagram looks like. So they do a nice job of documenting things for you here. And it says it implements the framework and schedule for the robotics program. You don't need to modify this VI. Actually, you need to just work in the sub-VIs appropriate to where you're working. So this is, it says begin. This starts at the very beginning to open I/O, initialize all your sensors and that sort of stuff. I'll show you what that looks like. Autonomous independent. It starts with the first packet of autonomous and aborted at the last packet. What that means is when the field that's controlling the robot says it's time for autonomous, it starts running that function. And when it says it's time for, it's not, it's the end of autonomous, it leaves this function and jumps into teleop. Disabled is what happens when the robot is disabled. The test is some others. You can do that for robot and sensor validation test. There's vision stuff you can run with the camera, and then we have periodic tasks, which run at user-defined rates, both during autonomous and during teleop. And then there's this finish you can actually call so that when you exit, if you hit that finish button that was on there, that'll actually save, you can have it save data to your disk and stuff. What's actually cool that a lot of teams don't use is that there's, a couple hundred megabytes of flash memory on that compact Rio that you could use to save diagnostic information, that sort of thing, if you really want. So you could actually have it, say, accruing data in an array over time, and actually just at the end of your round or at the end of your test cycle, you can actually dump it to the disk. It turns out that if you go through this cool thing over here, if you go to the National Instrument stuff, and there's this guy here called the Measurement Automation Explorer. This is something I use at work all the time. Is what I'll do is I'll actually write data on the compact Rio, and then you'll see this guy show up, right? This is the compact Rio. Now what you can do is, this is a pretty cool trick. You can do file transfer between the compact Rio and there's nothing on it. Nobody has saved anything on it right now, but you can see that there's a whole file system on there because it's running an operating system. So you can actually save stuff on here, and then actually transfer the files over to your computer and then read them there, which is pretty handy. I don't know if you guys have used that before.
I know. I think maybe they fixed it last year, but I know the year before, it used to store the error log in that flash memory.
Yeah.
But then if you got file overflow in the flash memory,
Yeah.
it would hang or do other weird things.
I think it writes over it now.
Yeah, that was really annoying because it was almost impossible to figure out what was going
Yeah.
on when you get the memory overflow.
Yeah, so you're right, you do have to be a little careful about stuff like that, but you can take stuff, these ones that we have for first don't have it, I believe, so from what I've heard, the one that we're getting in the fall will have this capability. It'll actually have a USB plug on it. Either you can use it in host or client, so you can either use a USB webcam, but you can also stick in a USB drive, and you can actually tell the compact Rio to save the U:/, and then it'll actually save whatever file you want up to the USB drive, which is my compact Rio in my lab actually has that, and so I take all this data with this thing, and then it just writes it all to my USB drive, and I'm like, oh, now time to go home and look at this data, and I can do that sort of stuff. So it's pretty handy for diagnostics. So you might say, well, in that round, when I was having these issues, what was my encoder actually doing? What was my thing actually doing? Rather than kind of, relying on your driver who's saying, well, it kind of looked like it was doing this from 50 feet away. It's like, well, you know, if you have the sensors on there, you can do a little bit more. Okay, so for example, on this, so you can see the test stuff. Let's look at what happens in, say, the teleoperated mode. So we can open this thing up and you can see there's a Boolean and a numeric and this sort of thing. We can look in here and you can see that it's doing some stuff with these different motors. And so basically you set references for the motors. So actually let's start at begin. I'm sorry, I'm a little scatterbrained today. Probably from giving 2 other presentations. Yeah, so you can see that here, in begin, when everything starts up at the beginning, when the stereo first turns on, it says, I'm going to set up in my brain that on the digital module 1 on here, on the PWM port 1, there's a motor that's connected to a vector speed controller, and I'm going to say, I'm going to call that one carriage. So this is called set ref num function. And so you basically assign that name to it. And same thing over here. Here I'm actually setting, this is basically an output to my motor. Here I'm setting up an input. Here they set up the camera. I didn't do this part, it was up here already. But here I'm saying, I want you to start up a digital input. It's going to be digital input 1. And here I want you to do number 2. There's this conversion thing that you need to use. And then you basically set up, I want to set up an encoder using those 2 inputs. Does everybody here know what an encoder is? So what an encoder is, if you want to come up here really quick, so that you can, if you haven't seen one before, if you come up here, you can see there's actually 2 on here. So this is an inkjet printer, like you might buy from Walmart for 30 bucks these days, right? This is actually a little older model. And so you'll see that it has a couple of components that are common with robots. So we have our motors here, right? So what an encoder is, it's a series of lines, usually on some sort of reflective or transmissive media. And you basically use an LED and then a light detector on the other side. And when that is dark, it says I'm on a line, and if it's not dark, then it says I'm between lines. So then it can count how many lines go by. So it's pretty cool. So on these printers, since they're selling the printer for 30 bucks, you can see here is this. This is the if you come on this side, this is the reading head for the encoder, and this little plastic disc has a bunch of lines that go all the way around, and that is actually the encoder. So as this thing, as the rollers scoot through this thing, this spins around, and then this spins around, and you can count how it spins. That is a rotary encoder. You can get them in different configurations. This is usually not what it looks like on the first robot. This is made to be as cheap as possible because they want to make all their money back on ink, right? And then this one, you can see there are a bunch of lines on this. This is a linear encoder, and so there's a similar read head on the back of this thing. And basically what it does is it counts the lines on that.
I guess that's for the paper.
Right, yeah. So this tells it how far it's moved on the paper. So it moves and then it slides back and forth and does its print, and then it moves and it slides back and forth. And the sliding back and forth is controlled by this little, or this guy here, which is the linear encoder. So that's basically that's how that. I like that because it shows you what the guts of an encoder are. When you buy one for first, oftentimes it'll look more like there's one on here. The connector broke off, but the encoder is fine. So this is an encoder you might have on your drivetrain. So this is a drive module you can just buy. It'll come with a mounting place for an encoder. You'll put that on there, and then this will basically watch the rotation in a similar way of this shaft. So if we wanted to count those rotations, or count how those blips went by, here I'm saying basically each blip is 0.1 inches, and I want to count in times 4 mode, which means each blip, I actually have 2 detectors on each channel, or for the lines. and they're offset by 90 degrees. So as they're offset, so as this thing goes by, so let's say this is my channel A, this is my channel B, so this is high and low, right? Does this make sense to everybody? So this is what's called quadrature. So they're 90 degrees out of phase. Out of phase meaning they're the same like waveform, but they're just offset. So you guys can see the offset. So and you can think of where the sensor is as one line like this. So as my wheel moves, this whole thing gets shifted back and forth. So if I'm moving this direction, right? If A rises and I look at B and B is high, then I know I've moved one blip in this direction. And if A is rising and I'm moving in this direction, then it will be going this way and B is low. So I can always tell which way I went. So basically if you watch both of the rising and falling edge and you relate back to what the other channel is doing, you can always figure out where you are and how much and what direction you went. Accurate to 4 times the number of lines you have. So if I run this thing, so what I have is I basically open it up. And so what's nice about the NI stuff is that they've actually set it up so that I can actually set this thing going and then it'll reset the encoder to count 0. And then after that, I just need to ask it what its value is and it'll tell me. So they've set all that counting guts up already and I'm just configuring it here. So let me close the begin one. And as you can see, that one will run before all this other stuff because I have this line coming out of here, and this line, this data, which is an output of this, is required before anything else runs. So by basically linking this line up, which is actually just an error signal, it even doesn't contain any data until, unless there's an error in begin. But because this can't run before it has that information of whether there was error or not, that's how they control when things execute relative to one another. That's one trick. Another thing you can do is you can use a structure called a flat sequence structure, and see it looks like a film thing. I can add frames, and what you can do is you can put stuff here and stuff here. The stuff that is in this frame will always run before the stuff in this frame. Then you could put a whole loop around this if you wanted to do stuff in sequence.
And you know the hard way.
Huh?
And I know the hard way, if you use those for timing critical things, it's a disaster.
Yeah, absolutely. So I try to get people to never use those if they can help it. But they exist. And there are some situations where they are the most reasonable way to go, but generally I try to avoid them as a rule. This is an example of a case structure. So it has, there's different modes here that you can configure, and depending on what mode you're in, which is set by this input here, it does different things. There's different things that it calls. But let's look at, since I'm a controls guy, I like to run feedback control stuff. So what I'm going to do is, right now, I'm going to set this to always output 0, so nothing is going to die, because sometimes this doesn't work correctly. But let's see what this loop does, right? It says that there's a wait of 25 milliseconds in here. This stuff runs pretty darn fast, so I'm not super concerned about that. It's really messing with my timing. But as a rule, you might want to do a control task in a loop like this. We have an output, which is my current position, and you can see that's related to my carriage encoder current coming in here. So I grab my name, and then this, and then it takes the reference of it, and then I can pull it out to the encoder thing and do stuff with that. Okay, I'm not actually using that thing, so we'll get rid of that. Okay, so what I can do is I can run this, and what will happen, and we can see that, So how did I set up that encoder? I set up my two digital inputs, and then I wired them into my open encoder. So I opened the inputs first and opened the encoder. If you don't open those inputs before opening the encoder, then it will try to read those inputs, but they won't be open, so it'll just show 0 for the encoder all the time. So now remember that this was in time tasks, so if we want to see, we can see what the current position is. Right? So I'm going to hit run on robot main, because if you run anything other than robot main, it will run only the sub VIs. So we want to run the entire robot, so I'm going to run that. It's going to deploy, so you can see now it's uploading all of my stuff out there. Let me turn this guy's screen on, and he says, oh, come on, man. You can do better than that. Sometimes this takes a while. It's a lot faster to just run it on the computer. But unfortunately, we don't have that option. This is why I do a lot of talking and not a lot of deploying over to the robot over and over again, because otherwise most of the presentation will be spent just sending code over. Somebody told me that doing it with Java or C++ transfers a little faster, but okay.
Of course, it decides to use 103% of CPU. That's another story.
Okay.
What was, I'm sorry, what?
We were using Dominant for competition. The VM ended up using 123% of CPU and shut a robot down in one of our key matches, and that was wonderful.
Probably not a good situation to be in. I can imagine. It was fun. We had a bad router and it kept dropping packets. Sort of, that was pretty miserable as well.
Our laptop also blue screened us. That's like another end. It's horrible. Our technology does not like us.
Yeah.
Doing the same thing.
Yes.
Good. How are we doing, buddy? Come on.
So you're gonna make that robot you put together last night work? Is that what you're doing there?
So what I'm going to show you is it reading the encoder that we just set up, and then we'll make it move around a little bit. Kind of,
But it's downloading the code
So-
to see real.
right, yeah, yeah. So this is the driver station laptop that we use. This is the programming laptop that we use. And I didn't, it's not wired right now. It's just wired.
Is there a reason you're using two separate laptops? Can you program and drive with the same one?
You could if you wanted to, but you have to keep switching user accounts.
But you still have to download the code to
Yeah,
the C
you-
real.
yeah.
It has to execute on the C real.
Right, yeah.
That's the slow part.
Yeah. Come on.
Could you have it like not deploy some of that stuff so when you're
Yeah, there are things you can play with and that sort of thing. You can also,
You saw it was downloading all that camera stuff.
yeah, I
That
was
took a
downloading
while.
all the
yeah. I just didn't want to delete it out of the thing because then a bunch of other dependencies get.
But like if you don't download the gate stuff, it won't work.
Right, yeah. The FPGA stuff, if you don't download it, won't do anything. It's just a really slow connection or something.
That's a pretty big program, actually. You're already at 75, 76% of capacity on the C real.
Yep. I honestly have no idea why it's taking so long. But that's okay.
But it is a lot of code.
And it's deploying the compressor code and stuff. I don't know
Right.
one of those. I don't know. Yeah,
Is there a version of LabView on the Mac with like full support?
not for embedded stuff. So the LabView real-time stuff is not supported on the Mac. LabView is supported on the Mac, so if you have a Mac with like USB data acquisition stuff that you were doing, say, for a science fair project or something, you could do it no problem. But yeah, the embedded stuff isn't supported on the Mac. Like right now, and the FPGA stuff is not supported on the Mac. The FPGA stuff is not supported on the Mac because the company that makes all the FPGA tools, Xilinx, doesn't make any Mac software. They have Windows and Linux versions. So that would be why that is. But for the embedded stuff, they just chose not to support it, I guess, right now. I know people who just run it in boot camp.
Yeah, I'm really tired of virtualization after like a few years
Okay.
of
Sure, or parallels, or, well, boot camp is,
It's on the
it's
actual.
just Windows. Okay, so, yeah, sweet, we have robot main, and you can see it's running, and in periodic tasks, think of it, enable, let's enable it, let's go into teleop, enable. So that current position has gone to 0, and hopefully, so I can move this thing, it will count, it's a little sticky, but it will count how much I've moved. So now I have a working encoder, woohoo! So now I have feedback that I can use for my control. So I'm going to make a small change, but it will probably take forever. I hope it doesn't take forever. Sometimes it takes a long time, and then it doesn't take very long. I don't know. Let's try it again. I'm going to change this back to like negative 0.6, and this is negative 0.6. These are just kind of made up numbers that I was messing around with. I built this thing last night, so cut me a little slack. So let's hit play. Come on, save that. Okay. Yeah, that's what I wanted. Come on. Oh, no, come on. Come on, buddy. Come on. Okay. So now if I go back to periodic task.